Welcome students, welcome to the next session of Strength of Materials 1. So in the previous classes we have already started our introduction for the flexural stresses, shear stresses and given the bending stress for overall depth and also the shear stress along the depth of any beam. Okay, therefore the shear stress distribution along the depth we have given that for the rectangular section, circular section, symmetrical I section, unsymmetrical I section and also in the last class itself we have completed shear stress distribution for the T sections. Okay. Now, in today's class, we are going into a triangular shaped beam. So, when we see or cut the cross section of the beam, you can observe a triangular shape for the beam. When you see the length, it is long body only. But when you see the cross section, it may appear like a triangle. Okay. So, the triangular sections shear stress distribution I am doing now. Okay. Firstly, the shearing force acting on a beam at a section is F. Okay. Only they have given in the things. Only F is the shearing force. And the section of the beam is a triangle. Okay, it is a triangle. Without mentioning anything, they have given it as a triangle. Okay, and the base is B and the altitude is H. Base is B and height or the altitude of the beam member is H. Okay, now the beam is placed with its base horizontal. Yes, I have placed this base as horizontal. On the horizontal plane only the beam base left. And find the maximum shear stress and also the shear stress distribution. Like the previous conditions, here also they are asking us to generate the shear stress distribution diagram for the triangular section. Like we already mentioned, as the section is not maybe symmetrical. B and H. Who said it is a symmetrical section? No. It may not be symmetrical with vertical, it may not be symmetrical with horizontal. See here, when you see any horizontal line, it is not symmetrical. For the vertical, maybe based on the dimensions, it may be symmetrical. So, this overall triangular section is unsymmetrical section. So, for the unsymmetrical sections, what is the first thing we should have to do? We should have to locate the neutral axis. Okay, so the location of neutral axis is important. And for the neutral axis location, what is a common point you can remember? The neutral axis is locating at the centroidal axis of the section. Okay, so for this section there is a centroid and through the centroid only the neutral axis will pass. And for the triangle with a base B and height H, what is the location of the centroid? So from the top it is at 2h by 3, from the base it is at h by 3. You can remember that, right? So that CG is at 2h by 3 from top, h by 3 from the bottom. As this CG is indicating the neutral axis line because the neutral axis is passing through the center of gravity. So the neutral axis line is located. After getting that, we can go into shear stress distribution. Okay. So we have given the base as B, height as H, and the neutral axis of the triangle ABC will lie in the CG of the triangle, as we have already explained. But the CG of the triangle will be at a distance of 2h by 3 from the apex or the top, and it is at a distance of h by 3 from the bottom. Anything you can remember, please don't remember both. Any one way you can remember. From the tip, that is at far distance. Okay, from the tip it is at 2h by 3. That is enough. Okay, from the top it is at 2h by 3. So that means the neutral axis will be at a distance of 2h by 3 from the top only. The next thing, consider a level EF at a distance y from the neutral axis. Yes, we should have to give the condition. And here, part by part the structure is not separated. So that how we have done for the rectangle, how we have done for the circular. Here also, for the whole structure I am considering a level. At that level I am generating the shear stress equation. Same like for the rectangular section, here also I am doing. Okay. So I am considering a level EF which is at a distance y from the neutral axis. See here, our triangle is there, indicated the neutral axis at a distance of 2h by 3 from the top, and from the neutral axis level at a distance y we have indicated EF line. Above that EF line we have given the shaded portion. Why that is needed? Because A into y bar is there, right? So for that A into y bar we have given the shaded portion. And then A into y bar, what it is indicating, that is moment of the shaded portion about the neutral axis. So moment of area of the shaded portion about the neutral axis is A into y bar. Okay, Firstly, we should have to calculate this. Why I should have to calculate that particularly? Because tau is equal to F A y bar divided by I into B, right? So F is shearing force acting at the section. A into y bar is moment or area moment for the portion above the level I am calculating the shear stress. So A into y bar is the area moment for the portion as I am calculating shear stress at the level EF. So above the level EF, what is the area is there? That area's moment about the neutral axis I should have to calculate. And I is moment of inertia of the whole section and B is width of the beam at the level EF. Okay. So all these things you should have to calculate. The first and the main thing to be calculated is A into y bar. Okay. I am going into that part. So that moment of the shaded portion for the about the neutral axis is equal to only this portion only I needed. Okay, so that portion C, E and F. The remaining I am not at all seeing, only axis and the area what I should have to consider. Okay, that is area of the triangle CEF. Yes, area of the triangle CEF A into y bar. Y bar means distance of center of gravity of this triangle from the neutral axis. Okay, so area of the triangle CEF into distance of CG of the triangle CEF from the neutral axis. Okay, how can I calculate all these things? Once you know any one measurement, the remaining measurements you can calculate. Then further, I am considering this we know as y, right? From the neutral axis, the EF level is at y measurement and the remaining height of the triangle I have indicated as x. Okay, so from the neutral axis level, EF distance is at y. From the tip, EF is at x distance. Okay, now from that half into area of this portion, half into base is E into F. Okay, that E into F into height of the triangle, that is x. So area into y bar. Y bar, how it will come? Y bar comes from when you know this total distance. Yes, up to the neutral axis I know it as 2h by 3 and up to this portion I know this height as 2x by 3. When the height is x, from the tip that is 2x by 3. When the height is h, from the tip that is 2h by 3. Okay, so that formula only invert. So 2h by 3, this is 2x by 3. What I need to know from this to this, how much it is left. So total of 2h by 3 minus of 2x by 3, that is y bar. So half EF into x, 2h by 3 minus 2x by 3. Now from this, and the EF is still unknown for us, right? So further I am using a similar triangle condition. Okay, so from the similar triangle conditions, what I can say? This is B, this is H, this is EF and it is X, right? So base, height. From the similar triangles of CEF and CBA, okay, CAB, anything, okay. This is bigger triangle and this is smaller triangle. Using these two conditions, what you can say, CEF and CAB, the measurement is base EF by AB, base by base, height by height, X by H. Base by base, height by height, or base by height is equal to base by height. Like that also we can write. Okay, so EF by AB is equal to X by H. My unknown is EF only, so I am separating EF from this. EF is equal to, and AB measurement. Anyone know AB? Yes, that is B only. So B times X by H. So EF value is B times X by H. So I can replace this EF in the next step. A into y bar is equal to half EF into x we have given, right? So bx by h. 2h by 3 minus 2x by 3 as it is, and taking the common out and multiplying with the similar terms, And we have got A into y bar is equal to 1 by 3 bx square by h minus x. And capital I is moment of inertia of the whole triangular section about its own central axis or the neutral axis. For the triangle of base B, height h, about the central axis, the moment of inertia is bh cube by 36. There, that is bd cube by 12, pi d power 4 by 64. This one is bh cube by 36. You should have to remember these terms. For a rectangle, moment of inertia b d cube by 12. For the circle, moment of inertia pi d power 4 by 64. For the triangle, about the central axis, moment of inertia, bh cube by 36. Okay. So, here I am using the triangular section. About the central axis, what is the moment of inertia? That is bh cube by 36. Okay. And the next thing is, next unknown is b value. F, ay bar, I and b. So, B is width of the beam at the level of EF. I am calculating the shear stress at level EF. That's why B means width of the beam at the level EF. That is EF. Just now only we have generated EF's answer. So this one only EF, right? From the similar triangle conditions, we have generated EF by AB is equal to X by H, and EF is equal to BX divided by H. So that EF is equal to BX by H. So from the basic similar triangle conditions, we have generated this B. So substituting all these things, we can get tau answer in terms of X. Okay. So when you see the whole picture, at the level EF, I am calculating the shear stress, and the neutral axis is, so EF level is at a distance y from the neutral axis, at a distance x from the apex, and the overall depth is h, base width is b, and from these two dimensions I have got the level EF measurement as bx by h, and the overall central axis is at 2h by 3. That is the neutral axis from the top. When you see from the bottom, that is h by 3. Okay, this is the conditions we are having. Now substituting all these values in the equation 1. What is the equation 1? That is the symbol tau F A y bar by I times B. So tau is equal to F A y bar by I into B. F is equal, so tau is equal to F into A into y bar. In the previous step only we have calculated I. Firstly I am keeping I as this, later will substitute because these terms itself are very big, right? So once this simplification was over, we can substitute I. And small b is width of the beam at the level EF. Don't keep that B as it is, because for our problem B is rectangle's base, sorry, that the triangle's base measurement. But this is EF, this is the B in the formula. B in the formula is width of the beam at the level EF. Okay, so that is Bx by H. So with the simplification and a small rearrangement, I have got tau is equal to F by 3I into Hx minus x square. Okay, so F by 3I Hx minus x square. This equation is important for us. I am keeping it as equation number 2. Okay, so tau is equal to F by 3I Hx minus x square. What it is indicating from the equation 2, it is clear that the variation of tau with respect to x is parabolic. Yes, because x is having second degree. So once x is 1, corresponding x squares relation only tau will get. So x and tau are having a parabolic relation. Tau is relation with x square, second degree equation relation, so that the answer is parabolic. Now that is the equation for shear stress at any level x from the top. The answer is tau is equal to F by 3I Hx minus x square. So whatever x you substitute, the corresponding tau it will get. Once x, but the x is measured from top, from our explanation. Okay, so when you see any point from the top, at that point I can calculate the shear stress using this formula. Okay, so at the top, that means x is equal to 0 level. X is equal to 0 level. What it is? From when x is equal to 0, it indicates, substituting this answer, we have got F by 3I 0 minus 0. So the corresponding tau is equal to 0. as we already know, at the extreme top edge, the shear stress is equal to 0. Cross check is also happened. Now, when x is equal to h, h means when I am reaching this level, okay, measured from the top, but I have reached to base, then x becoming h. So, when we substitute h, tau is equal to f by 3i h square minus h square. This f by 3i into h square minus h square, that is equal to 0. Okay, so at the bottom at x is equal to h, the tau is equal to 0. Any other point left is at the neutral axis level, right? So now the shear stress at the neutral axis level. Where the neutral axis is being located? From the top, that is at 2h by 3. Again I should have to substitute from the top only, right? So this measurement is 2h by 3. For our formula, x should be measured from the top. So the corresponding top answers only I am giving. Okay, from the top, top edge, from the top, bottom edge, from the top, neutral axis. Now from the top, neutral axis is at 2h by 3. Now substituting in this equation, we have got after the rearrangement f by 3i 2h by 3 into h, hx minus x square, right? So and for us h is equal to 2h by 3 now, as the neutral axis is there, and I is equal to bhq by 36. So here I am substituting, because in the previous step I substituted also 0, 0 answers are there. So I am not using, and here I am substituting, and we have got the rearranged answer as 2 by 27 fh square bhq by 36, and finally tau is equal to 8 by 3 f by bh. This is the shear stress at the neutral axis level. So this is the shear stress at the neutral axis level, which means at x is equal to 2h by 3 level, this is the shear stress. Generally, the shear stress will be maximum at the neutral axis, but only for the triangular sections, shear stress is not maximum at the neutral axis level. It will be somewhere else. So, when we need to calculate what is the maximum shear stress location, what we should have to do to make anything maximum, we should have to differentiate and make it equal to 0, right? So, as I need to make the shear stress to be maximum, I should have to differentiate with respect to x, and it should be equal to 0, so that I can get where, at which location the shear stress is maximum. Okay, now the maximum shear stress, that is the shear stress of any depth x from the top, is given by equation 1. Yes, that equation 1 only we have got. Tau is equal to f by 3i hx minus x square. Okay, so the shear stress of any depth x from the top is f by 3i hx minus x square. Now the maximum shear stress, how we will get? We will get by differentiating the equation with respect to x and making it equal to 0. So d by dx of the function which is equal to 0. As I already know, f and I are being constants and keeping the same as it is. So what it will give? This is nothing, constant, and hx minus x square. So coefficient of x is h. So h remaining and 2x is remaining. This is not there, or you can keep it as it is also. It is just a coefficient value, f by 3i x minus 2x, h minus 2x, and multiplication, this is 0, and x minus h minus 2x is equal to x is equal to h by 2. Now, what it is explaining? The maximum shear stress is occurring at h by 2 from top, not at 2h by 3 from top. 2h by 3 is neutral axis location. But here the maximum stress is at some other point which is h by 2. Now, at this level I am calculating the shear stress. So, substituting this x is equal to h by 2, that tau maximum, here before was tau at the neutral axis level. This tau maximum is equal to substituting in the equation 2 f by 3i hx minus x square. So substituting that x answer is h by 2, and we have got the answer as 3f by bh. There 8 by 3 f by bh. So when you see, this is 9 by 3 times. So this is, I can write as 9 by 3 F by BH. This is 8 by 3 F by BH. Sorry. So compare these two. This is the higher value, or 8 by 3 ratio also you can observe that is lesser than 3 value. Okay. So the maximum shear stress will be like this. Now I am distributing or generating the shear stress distribution for the triangular base. So we are having the triangular section with base B and an altitude as H. And we have indicated our nodal axis, which is being located at a distance of 2h by 3 from the top. But this is not the maximum location. Some location is there that is at h by 2. Only this point is helpful for us for giving the shear stress distribution diagram. Okay, so I am indicating that, and at the top, complete bottom is 0, and at the neutral axis level we have got some value, at h by 2 also we have got some value, and indicating those answers here we have got as 8 by 3 F by BH, and at h by 2 we have got as 3 F by BH. And connecting these points, we should have to follow a simple parabolic law. Connecting this to this and to this, and with a free hand. No need to separate like this. Only with a simple free hand you can go. But at the neutral axis that is not maximum, at h by 2 that is maximum. Okay, when you see the whole picture, it may appear like this. At h by 2 tau maximum is happening, and at the neutral axis some other value is happening that is not maximum. Okay, so when you see the whole picture indicating the neutral axis, indicating the h by 2 level, so we will get the shear stress distribution diagram for the triangular section. Okay, so in the next class we will go into the next chapter. Thank you so much for the session, and with this we are concluding flexural stresses and shear stresses. Okay.